As Alex mentioned, my name's Nick Hibbard. I work at Ambiata and I am a data lake fisherman. So for those of you who don't know what a data lake fisherman does, my job basically consists of copying bits from one place to another so that we can solve interesting machine learning and data science problems. Now, copying bits sounds easy, but at scale it means variable workloads, starting and stopping hundreds of servers a day, as well as maintaining a 24/7 farm of web services and applications that are continuously being redeployed. So you can see the job of a data lake fisherman becomes quite challenging very quickly unless we can tame infrastructure deployment. We utilize Amazon Web Services quite heavily, mainly because the requirements on our infrastructure are highly elastic. We can be running thousands of servers when we're processing data, and when we're not, we try to have as close to zero running as possible. We simply couldn't afford the hardware costs associated with maintaining our throughput bursts. So there are a variety of problems that we have to solve, and our first problem today is batch processing. Most people have some form of batch processing, whether it's an email server or some form of backup. At Ambiata, 90% of our batch processing is around data transformations and machine learning. So what are the properties of batch processing? Batch processes start, they run, and they stop. They don't run continuously. This means they can be running for 3 seconds on a single server, or for up to 3 weeks on a cluster of servers. And generally with these processes, we value throughput over latency. At Ambiata, the challenges of batch processing are configuration and data management, as well as the tracking and improvement of our processing costs. Batch processing costs for us are a significant proportion of our operating costs, so any improvements can be significant. Our second problem is online processing. The most common form of online processing is standard web applications and services. This is also true of Ambiata. So what are the properties of online processing? Well, firstly, online processes run continuously. They don't start, run and stop, or give us an obvious opportunity for upgrades like batch processes. And generally, we value latency over throughput. At Ambiata, the challenges of online processing is continuous deployment without downtime. To give you an idea of that problem, we have hundreds of repositories. We don't have a dedicated operations or support team, so we can't really afford to have a human involved in this process, which also makes it quite challenging when we're trying to automatically deal with failures and rollbacks. The final problem we worry about today is leasing, and this is not a problem that a lot of people have. But at Ambiata, we have people whose job it is to work in production, data scientists, data engineers that are working with online data sets that require production managed servers and tooling. So what are the properties of leasing? Well, leases are simply a person's claim to a resource for a period of time. Leases should be exclusive, meaning they shouldn't be used by any other processes, human or automated. Leases should be isolated, meaning they can't interact or interfere with any of our automated systems. And finally, leases should default to termination and automatic management. This is important because we can't allow a human to forget something that it will end up costing us money. So our problems are at the scale where there are both financial and commercial benefits for solving them. At Ambiata, we write the majority of our tooling with functional programming ideals using Haskell as the implementation. However, this doesn't just mean that we're a single language shop, but the majority of our code is in Haskell because it suits our problems. So why do we choose Haskell in functional programming for our particular problems, or these particular problems? Well, dealing with complex systems is hard, and infrastructure deployment is a complex system. So Haskell, its type system, and its functional properties help to make this easier to deal with. So let's start off by walking through how we configure and launch servers with Haskell. We start by defining all of our operational configuration in plain Haskell data types. We didn't feel the need to invent something new or use an external DSL to do this. And it's not that we're afraid of doing something like that, it's just that we felt that using an embedded encoding with Haskell's flexibility is the best way to deal with it. So once we've defined all of our operational configuration, we type check it, serialize it, and publish it to a store where we can treat configuration like artifacts. Then for every server that we start up, we have a small daemon written in Haskell running, which reads that configuration and then manages the lifecycle, monitoring, and registration of notifications for that service, or server rather. So now we're going to walk through our solutions. And our current solution is the result of several evolutions. In the outset, we solved all of our problems individually, which meant that all of our solutions had an individual set of servers and infrastructure. However, over time, we've developed enough insight to see a unified solution for batch, online, and leasing. In our architecture, there are three types of services that contribute to our infrastructure deployment. Our base service is our lifecycle management service. We think about lifecycle management as providing a set of capabilities, where each capability is a set of servers with their resource types, permissions, and configurations. Internally, we refer to our service as AMP, and AMP gives us the knobs to control these capabilities without having to worry about how we start or stop servers. This means that we can easily scale up or scale down the capacity for our current capabilities. The next set of services are our scheduling services. And scheduling is mainly about managing a number of constraints around cost and time. The unit of scheduling is a task, and scheduling involves both controlling the configuration knobs for our capabilities, as well as efficiently handling task allocation to those capabilities. So tasks need to define the scheduling constraints and resource configuration so that the scheduler knows what capabilities they can run on. Tasks also need to define what, if anything, needs to be executed after that task has been assigned to a capability. So when a task is submitted to the scheduler attempts to find a capability that meets that task's requirements. If it finds that capability, it will then allocate that task to a resource under that capability. However, if there are no resources under that capability, the scheduler controls or manages how that capability is scaled. And the scheduler can also make decisions around when to delay task allocation due to things like high resource costs. Our final and most interesting set of services are what we call operational services. The purpose of operational services are to both submit and monitor tasks. And unlike lifecycle and scheduling, which are centralized services, we have a number of different operational services for dealing with our different problems. Our first operational service for dealing with batch processing, we internally refer to as Hydra. And you can think of Hydra as distributed cron with a few cool extra features like dependent tasks. Our lifecycling and scheduling services mean this is a fairly trivial exercise, so I'm not going to go into a lot of detail. But we'll start with our Hydra configuration, where we define our tasks in plain data types. So here we have a job which runs daily at 9:30 in the morning and executes some command. And as I mentioned, Hydra has a number of different mechanisms for scheduling. So, triggers rather. So when the requirements for one of these triggers is met, then Hydra simply submits the task to the scheduler, and then at the appropriate time begins monitoring that task. Our next operational service, and potentially most interesting, is our continuous deployment system. For every server that we have configured to be continuously deployed, our deployment starts with a commit. That gets picked up by our CI server and built and published to a store. And as a deployment system, we see this new version of software in our store and we decide, well, let's start a server up and put that software on that server. And potentially we're interested in things like reliability or robustness, so we actually decide that we want 2 servers running with our piece of software. It's all well and good to say that, oh yes, let's start up some servers with some configuration. It's not really that interesting unless we can say that, yes, those servers have started successfully. If we just deployed a web server, is it returning 200s or 500s? If we can say that we've successfully deployed something, it's running the way we want it to run, and we can notionally say that our servers are healthy or active, then we can finally say that we've deployed our version of software. And this is the same process we go through for deploying all software in our system. So where do we start building our solution? I like to start with the perfect program. And this program just simply reads in some real-world state, passes that state into our pure calculate function, which calculates a new state, and then we update the world with our new state. So how do we go about describing updates to the world? We simply need to encode every step in our lifecycle deployment process we went through. The first thing we wanted to do when we were creating our server was establish a task with our given configuration. The next step was to establish a second task with that given configuration. Then we said we wanted to be able to change the lifecycle status of our tasks. We wanted to make them healthy. Something we didn't mention is our failure. But given that we're talking about our pure calculate function here, we need to encode a way to say that, well, our servers haven't actually started up successfully, and then let our update interpreter handle that later on. And finally, when your entire engineering team is at ICFP and CUFP, then no one gets to write any code and you do nothing. So now that we know what we want to calculate, let's have a look at the calculation function. First, we need to be able to make a few decisions. We need to be able to say that we haven't made a decision yet and we should keep going until we do. Or potentially we have made a decision and we should stop and do that, we should terminate early. Or for some reason our system is in a bad state and we should stop anyway, it's not safe to continue. Result here is also a valid monad, and I raise it because it's interesting that both success and failure are terminating cases, and no result is our continuation. So we also need a few combinators to help build up our deployment DSL. First off, we just have this success combinator which takes our goal and lifts it into our terminating success. And we have this with combinator, and the implementation is not that important, but you can think of it as running a query, and if that query returns a result, then we'll run an action. Otherwise, we'll keep going until we can make a decision later on. So now that we have our building blocks, let's deploy our first service. We said that we wanted to establish a task of count 1 with our configuration. Implicitly, what we didn't say earlier was we only want to do this when our version of software is not currently deployed. In other words, when there are no matching versions running. So how do we actually work out if there's a matching version running? Well, over time we've learned that it's hard to individually deal with all the parts of the configuration that goes into a server. You have software, users, permissions, other metadata, and it becomes a really complex piece of state. So the way we deal with this is to condense things into a fingerprint. And a fingerprint is simply where we take our interesting pieces of our configuration and compute their hashes to calculate our final fingerprint. This has given us some nice properties. Like for example, if we wanted to have a stable release server where we didn't deploy a new server for every single piece of software that was in the store, we could simply omit the list of software from our fingerprint. Or maybe we wanted to roll our server every single day. We could add a date into our fingerprint, which would generate us a new hash. And therefore, we'd get a new server every single day. So our no matching versions function then becomes very simple. We just calculate the fingerprint for our configuration and the fingerprints for all of our tasks that are running, and we see if there are any matching. So now we know how to calculate versions. Let's have a look at version 2 of our software because we always end up writing more code. So we simply have to follow the same process that we did earlier to create our new group of tasks. When we finally have that group of tasks deployed, we can think of version 2 as our, we can think of version 2 as our group of desired tasks or desired tasks here, which allows us to run a number of operations over them. So when our group's under capacity, meaning that simply the number of tasks running is less than our desired capacity in our configuration, then we can increase that capacity by establishing a new task. Or potentially, if we were over capacity, we could decrease our number of established tasks. Earlier I talked about failure, and we also need to be able to handle that. So when our servers haven't started up successfully, we want to stop and say they're not yet healthy so that we can get some type of person involved. So here we have all of the operations over our desired tasks. So now that we have our second version of software deployed, we don't really need our first version anymore. And we can think about version 1 as having our most least desirable tasks that we can begin to shut down. Unfortunately, we can't just flick the switch and turn them off. We may have things deployed like web servers that have in-flight connections, so we need to at least tempt a graceful shutdown. We do this by updating the lifecycle to be inactive. This could mean removing load balancers from in front of those servers or simply just sending a notification to those servers. And then finally, after enough time has passed and those servers are inactive, then we can flick the switch and we can turn them off. So now we have our continuous deployment program written in our DSL. Yeah, so now we have our calculate function. What does our update interpreter look like? Well, our update interpreter is quite simple. It simply needs to take our goals and submit those decisions in the form of tasks to our scheduler, which turns out to be remarkably similar to how we solve batch processing. Our final operation is about leasing, and I'm not going to go into a lot of detail, or any detail rather, because our lifecycle and scheduling services make this so trivial. This service simply needs to submit a task to our scheduler in the form of claiming a resource for a period of time upon request from a user. So there are a lot of tools that try to solve similar problems. However, they all bring their own levels of complexity, and they also don't quite have the same properties that we desired. And in an environment as complex as ours, they would end up leaving us in a toxic spot. So we've invested a whole lot of time and effort using a whole bunch of different techniques to solving these problems well. And in our environment, this has paid off considerably. So hopefully some of these solutions or ideas can be useful to others as well.
I'm Dan Kerrigan from Fugue. How do you determine the resources that will be required by the software that is being deployed to an instance, and then incorporate that metric data into the scheduling process?
So in our task definitions I'll try to go back, might be helpful. A lot of slides. Scheduling, task definition. So in our task definition, so when we submit a task, we have our resource constraints and configuration. So here's an example. So we have a disk constraint, which is 100 gigabytes, and we want our CPU to have an instruction set of AVX2. So we take that, and then we know what our resources have. We know that this server has this much RAM, or this server has this instruction set. So it's a reasonably easy function to calculate from that point of view. Does that answer your question? Thanks.
So how do you persist the state of things in case your like tracking system goes down? Like it just gets, power cord gets kicked out or something.
So in terms of the scheduling or the continuous deployment, or
The scheduling itself, yeah.
right?
And then resource tracking.
Yeah, sure. So we rely on Amazon to do that for us. So we use DynamoDB. Yeah,
That makes sense, thanks.
yeah, nice.
I'm curious what led Ambiata to adopt Haskell in the first place.
In the first place, that's a good question. It's probably a long discussion. Maybe we should have offline, but yeah. Is that all right? Yeah.
So you said that those ideas could be reused by other people, but why not open source that as a coherent system and way of doing things?
Yep. We should open source them. That's true. We could right now, technically, but in reality, they're probably not useful to anyone else because there's a lot of other infrastructure around the place. But as a source of ideas and such, that would probably be a good idea if we get some time.
Let's thank our speaker again.